All right, so analyzing graphs of functions and relations. When you look at a graph, it's going to give you a lot of information about what's going on with whatever function they've given you. The graph of the function is just a set of ordered pairs. So if I look at this function, I'm just saying here's an xy, here's an xy, here's an xy. If you have arrows at the end of it, it goes on infinitely. So there's an infinite number of xy's that have been plotted here that create this graph. The domain for the graph is the x values that you can put into it, and the range is the y values that you can put into it. And of course, your x value is just your distance from your origin, right and left, and your y value is your distance from your origin up and down. Let's look at the first example here. It says, consider the graph of function r, which is shown. What they're talking about here is internet ads revenue per year. Year since 1998. This makes sense that it's going up, right? And total revenue in millions is on the left-hand side. So when you look at a graph like this, you want to make sure that it is labeled. Without labels, it doesn't mean anything. If they don't tell me that that means years and that means revenue in millions, I will not understand the graph. Very important. And this is also a logical thing you need to look for when you are given a graph, whether it be, in paper, in print, or on a news network. It's really important that they tell you what that graph means, because if not, they are not giving you all the information to make an educated understanding of the graph itself. So it says, use the graph to estimate the total internet advertising revenue in 2007. Confirm the estimate algebraically. All right, so they have given us the actual function, by the way. If I were to look at this graph, 2007, this tells me it's that many years since 1998. So how many years since 1998 is 2007? 9. So there's my 9. And so I would take this graph and I would go all the way up here, and I would say that's where 9 hits, and I'm going to go across, and I would say that is my estimation. So my estimation here would be what? About maybe 30, let's see, that middle mark is 35. So 33, 34, somewhere in there, right? Does that make sense? I think they estimated it at 3,300 million is what they estimated it in the book. That's a lot of million. That's what they estimated it. Now, if I have the function, which they give it to me, and we're not going to, when they actually, I will let them plug it in, because that's just a lot of, this is the actual function that they gave me. 17.7x cubed minus 269x squared plus 1458x minus 910. So they gave me this function, and now they just plugged in a 9 to see what it actually is. And it ends up being like 3.326 billion, which they were just a little bit off when they did 3,300 million. That's 3.3 billion. So they were very close in the estimate when you look at the graph. Here's the thing. Graphing is a visual representation, but unless you are tracking it on a computer and the computer tells you exactly what your X and Y value is, all you're doing is estimating when you're using a graph, okay? Same thing when we solved them by graphing, right? When we solved the 2 linear equations by graphing, if you didn't draw those perfectly, you might not fall on the crosshairs of an XY, right? And so that's the same thing that happens with graphs. You have to be very careful when using a graph, because it is just an estimation. And that's why they said estimate the total. That's why they gave this word right here, because they wanted to make sure you knew you weren't giving an exact amount. All right, so that is if they're saying, okay, this is how many years it is, now estimate the sales. Now they're saying use the graph to estimate the year in which the revenue reached 2 billion. So this time we're actually going to go to our y-axis, all right? And we're going to say, well, where's 2 billion? 2 billion is right here. And so now I'm going to go the other direction, and I'm going to say, well, they want to know when it reached 2 billion. So if I were to do this, it goes about right there. All right, now you'll notice that somewhere in between 5 and 6, it would have reached 2 billion according to the graph. But if you look at it algebraically, it actually falls closer between 6 and 7. It actually falls over here. So that's why they have that line. And so it depends on what they've given you. You've got to make sure you know, did they give me my X value and they want me to give the Y, or did they give the Y value and they want me to give them the X? All right. So let's look at the top of page 16. They want me to use the graph to estimate the value of the stock. I am not going to make you confirm it algebraically at this point. All right. I just want you to estimate it. And you use the graph to estimate the days during which the stock was valued at $30 per share. So you don't have to plug it in. You're literally just using the graph here. All right, let's look at the first question. Use the graph to estimate the value of the stock on the 10th day. The 10th day. So I'm going to go to day 10, and I'm going to go right here. All right. So approximately what would the stock have been on the 10th day? Maybe about 32, right? And then it says use the graph to estimate the days during which the stock was valued at $30 a share. $30 a share. So now I'm going to look at the Y values. So 30, it looks like it started out on 30, okay? We know it actually started out on 31 based on the algebra equation, but I would say somewhere around that day. And then we have maybe day 9, somewhere there. And then we have about day 15 or so. Day 15 or so. So there are multiple times that it hit 30. Obviously, stocks go up and down. All right? Domain and range. So the other thing that graphs help us do is they figure out if there's problems in the graph that we can see visually. So we've already talked about problems in the graph when they just hand you the function, right? If there's a 0 in the denominator, if it goes negative in the square root, right? Those are problems in your domain or limitations on your domain. You can also see limitations on your domain when it comes to graphs, all right? And so if I were to find the domain and the range here, the domain and the range, I am looking for my X and Y's, all right? So let's look at domain first. Domain are my X's, right? Remember there's a one-to-one relationship, all right, from X to Y. So if I'm looking across here, do I see anything in the graph that stands out? When I look at the graph itself, is there anything that stands out about this graph that looks different?
It hits the axis more than once.
It does. It hits this axis more than once. That's true. Are there any, does it look like there's any breaks in the graph? That is an open hole. Okay, so there's a break in the graph. We have a break in the graph right here. That is an open hole right there. Okay, so that means I have something that causes a problem with my graph. All right. So for my X value, if I look at 4, -4 specifically right here, I do not have a value for -4. If I put a -4 in, I don't get a value out. There is no Y for -4. There's a hole there, okay? So that tells me for my domain, X can be anything right here except -4. I also want to point out one more thing. This down here stops. You see there's no arrow, right? So that's the end of my graph. So I end where? Well, I end right here. Does that make sense? So from -8 to positive infinity, that would be my domain, except for one little number, -4, right? So if I were to write that in, let's say, interval notation, I can say, well, it starts at -8. Does it include -8 or not include it? Is it an open or closed circle there? Closed. So it should look like that, right? And I can go all the way to -4. All the numbers in between -8 and -4 work. Does -4 work? No, so I'm going to say open there. Everybody see that? And then I'm going to do a union there from -4 to where? Where does it end? Does this graph end on the right? It doesn't, it keeps going. So how do I write that? Infinity. Make sense? So when I'm looking at domain, I'm just looking across, okay? Now we're going to look at range. That is up and down, okay? That's up and down. So if I were to look at range here, that is my domain. We're going to look at range, all right? So we're going to start down here. Does it go infinitely down? No. Where does it start? Right here, but now we're talking about my value here, right? Talking about this value. All right, so when I talk about that value specifically, my y value, -9, right? So my very lowest point's -9. Does it include -9? Yes, it does. Now, let's go up from -9 because it starts here. We know it eventually goes to infinity, right? We know there's a problem here at 4 on this side. But is this defined at 4? Over here it is. I don't jump out of 4, right? The y can be 4. There's not a problem with it being 4. Is there any number from -9 up that causes a problem that you can see? Where it doesn't have an x value? No. So I'm just going to write infinity. Open or closed with infinity? Open. And that would be my range. So when you're looking at your domain and range with a picture, you're literally looking, is there a problem? Does it start and stop somewhere? Like we have it here. It doesn't go infinitely down. How do I tell you that? How do I tell you it doesn't go infinitely down? All right, let's look at these together. Domain. So your domains, they have -6 to 2. Well, let's walk across this x-axis. Where do your x's start? Well, they start at -2, right? These are every 2. They start at -2, and they end at +6. It includes -2, closed circle here. It does not include +6, open circle. So I have a closed bracket at -2 and an open parentheses at 6. Let's look at my y values. So I'm going from the bottom up, right? I don't have any y values down here, right? I don't have any y values down here. Where do my y values start? At 0. And they go all the way up to here, which is 4, right? It includes 0, right? Because there is a closed circle here. It includes 4. So bracket, bracket. Make sense? All right, let's look at this one. So I'm walking across the x-axis for the first one, walking across the x-axis. There are no x values back here. I don't get an x value until -4, right? And it is an open circle, so that is parentheses. -4, all the way here to +2. Also open circle both places, right? So parentheses there. Then I'm going to union that with +2, and it goes on infinitely. So open parentheses, 2 to infinity. All right, let's look at my range. All right, my range. I am all the way down here at -infinity, and they actually did it this way because they actually wrote it from the top down. If you wrote it from the bottom up, you probably wrote -infinity to -2 and then 6, which is fine. They just did top down. So we can see that from -infinity to -2, we have y values, right? And then we have this random y value at 6. So they just said 6, and then the union between -2 to -infinity. All right, so we've done y-intercepts. Y-intercepts where it's across the y-axis. We did that with linear equations, right? That's how you graph a linear equation. You find your y-intercept, you use your slope to walk, all right? You also can have x-intercepts, and so that is where it crosses the x-axis. For a function, you will only have one y-intercept. You will never have more than one. If you have more than one, you do not have a function because that means you have 2 y's for the one x value of 0, okay? However, you can have multiple x-intercepts because it doesn't matter if you have the same x going to the same y, right? I mean, a different x going to the same y. So x-intercepts, you can have as many as the graph gives you, okay? How you find them. Graphically, it's easy. You look, right? Y-intercept, here's my y-intercept. If this had units on it, I could tell you what the y-intercept is. It's always going to be 0 and then whatever number this is on the y-axis. X-intercept, if you're looking at a graph, it is where it hits. This is always going to be some number and then 0 as your y. So wherever it hits, you're going to have your x-intercept. If you're finding it algebraically, you are just going to put those zeros in. So to find the y-intercept, you put zeros in for all of your x's and solve, and that is your y-intercept. For x-intercept, you put a 0 in for your y and solve. Now you may have to factor or whatever because you could have multiple x-intercepts, right? But you just plug in a 0 for your y and solve for your x, and that is your x-intercept. So let's look at example 3. finding this. Use the graph of the function to approximate it, then find it algebraically. All right, so if I were to look at this, my y-intercept here, I'm assuming these are 1, 2, 3, 4, and so on and so forth, would be about, what, 1 1/3. Everybody see that in your book? So I would say my y-intercept is probably, if I were to estimate it, approximately 1 1/3 for my y-intercept. And then for my x-intercept, I'm going to say about the same thing. So it appears. Oh, we're just finding y-intercept. That's good. All right, so we're just finding y-intercept. So about 1 1/3. So then how do I actually find it? They want me to also find it algebraically. So I have f of x equals negative 2x cubed plus 4 over 3. If I'm finding my y-intercept, I'm going to plug a 0 in for my x. 0 cubed is 0 times negative 2 plus 4. It is 4/3, right? So I know that my y-intercept is going to be this point right here, 0 4/3. So graphically, you're just looking. Algebraically, you're just plugging in a 0. And I will tell you that I always have you find it algebraically. I want the exact value, all right? So look at the next one. If I'm estimating, I am going to say this should fall at 4, right? It looks like it falls at 4. Let's plug it in. G of 0, I'm plugging in a 0 for my x. 0 minus 5 minus 1. 0 minus 5 is negative 5. That is absolute value. So the absolute value of negative 5 is 5. What are they? Oh, I put 4. All right, helps to write the problem. I was doing the math in my head and not. Minus 1, and that is 4. All right, so when I look at it visually, it looks like 4. When I plug it in, it's 4. All right, so for these two, I want you to find the y-intercept algebraically. Find the y-intercept algebraically for both of these. One, finding a 0. All right, the term 0 is the same thing as x-intercept. So when you hear find the x-intercept or find the 0, that is the same thing, okay? So when you see find the 0, they just want you to find the x-intercept. So if I solved for the y-intercept, plugging a 0 in for my x, then when I'm solving for the x-intercept, I am plugging a 0 in for my y. Now, this particular function, I don't see a y. What is my y here? That's my y. F of x means y. All right? So, if I'm plugging a 0 in for my y, I'm actually setting the function equal to 0. All right? Now here, I actually have to factor this. Everybody remember factoring?
Yes.
All right, so this is going to factor 2x minus 5, and x plus 3. If you don't remember, you can do the 30, right? Factors of 30. That give you 1, and then you can do 2x squared plus 6x minus 5x minus 15, and factor by grouping, right? If you don't remember how to factor. But you're looking at factors of 2, factors of 15, and you're going to mix them together to get your terms there. Once I have that, what do I do with these two? Set them equal to 0. I'm trying to figure out where it equals 0, right? Solve this guy. Add your 5 over. And then divide by 2. So x equals 5 halves, or 2.5. Same thing. Over here, you just have to subtract a 3. So x equals negative 3. So my two zeros here are 5 halves, 0, negative 3, 0. All right? Which you probably wouldn't be able to see that just looking at it, because visually that's hard to see. So y-intercept, plug a 0 in for x. X-intercept, plug a 0 in for Y. And X-intercepts are also called zeros. Okay, X-intercepts are also called zeros. All right, the other thing that we look at when we're looking at graphs is, are they symmetric? What does symmetrical mean? It means that wherever your reference point is, it's the same on both sides, okay? So like a circle is symmetrical all over, okay? If I were to draw a triangle, this is symmetrical this way, right? But it is not symmetrical this way. Nope, I can't do it that way. A circle is symmetrical both all around, right? X and Y. And so we actually look for that compared to the X and the Y. They give you 3 different types of symmetry here. 3 different types of symmetry. The first thing is it can be symmetric to the x-axis. It can be symmetric to the x-axis. It is symmetric to the x-axis if every x and y gives you an x negative y. All right? So if you have an xy up here, then you have an x negative y. Now this one's not a function, it's a relation because it doesn't pass the vertical line test, but it's symmetric. It is symmetric to the x-axis, If it is symmetric to the y-axis, then for every positive xy, I have a negative xy. All right, a negative xy. And then if it is symmetric to the origin is right here, okay? Then I have every xy is going to also have a negative x, negative y. So how do I do this algebraically? That's exactly what you do, all right? For symmetrical to the x-axis, you can plug in a negative y to your function, and it should be exactly the same as it was before. It shouldn't change it, okay? If you're looking for symmetry to the y-axis, you can plug in a negative x, and it won't change your function. And then if you're looking at origin, you can plug in a negative x and a negative y, and it won't change your function. All right? So let's look at when this happens, okay? Let's look at when this happens. Look at the top of page 17, example 5. All right? So they want us to tell them if it is symmetric to x, y, and origin, or it could be symmetric to multiple ones, okay? So if I am looking for symmetry to the x-axis, then for all of my y's, I am going to plug in a negative y. So I'm going to say x minus, and instead of y, I'm going to write negative y. What happens when I square negative y? What does it become? Just y squared, right? Is that the same as my original function? Yes, x minus y squared equals 1. That is the same. Don't you agree? So yes, this is symmetric to the x-axis. That is symmetric to the x-axis. If you look at it, you can actually see it symmetric to the x-axis, right? Visually. All right, if I'm checking my y-axis, I am going to replace my x with a negative x. So I'm saying negative x minus y squared equals 1. Is that the same as my original function? No. This is not symmetric to the y-axis. Not at all. All right, and you can see that visually, can't you? That it's not symmetric. Let's look at origin. For origin, I just replace both. Negative x minus negative y squared equals 1. I can simplify that to look like this. Is that the same as my original function? No, I have a negative x there. So this is only symmetric to the x-axis. That has x-axis symmetry. Everybody see that? So do B. Do B algebraically. Algebraically, do B. Is it symmetric to the x, y origin or multiple ones? So let's look at that one. When I plugged in a negative y, I got a different. When I plugged in a negative x, I got a different. But when I plugged in negative x and negative y, it ended up being the same. So it is symmetric to the origin. It is symmetric to the origin, which you can see from the picture. All right? There are situations when it will be symmetric to everything. Look at your guided practice down there. Guided practice. Look at 5B. 5B is symmetric to everything. When I plug in a negative y, I end up squaring it, and it becomes just y squared. When I plug in a negative x, I square it. It's positive x squared. And then when I plug in both, so that circle is symmetric to all of them. Now, I will say not all circles are symmetric to all of them. If that circle moved around the graph, it would not be symmetric. But because it is right on the origin, the center is the origin, that circle in your guided practice is symmetric to everything. And so if you look at guided practice, you can see visually that it is symmetric to everything. X-axis, y-axis, and the origin. But if you look at it algebraically, you can see that those squares are going to make them go back positive. And so even algebraically, you can show that it is symmetric to everything. All right, the last thing we're going to talk about are what's called even and odd functions. Even and odd functions, all right? If it is symmetric to the y-axis, it is called an even function. So once you test for symmetry, you can then tell me if it is an even or an odd function because you've already done the test for it, okay? So if it is symmetric to the y-axis, it is called an even function. If it is symmetric to the origin, it is called an odd function, all right? So if it is symmetric to the y-axis, it is an even function. If it is symmetric to the origin, it is called odd. So when I ask you like a multi-part question and I say, test for symmetry, tell me if it's even or odd. That's not two different things. You're going to test for symmetry and then you will immediately be able to tell me if it's even, odd, or neither. Okay? If it is symmetric to the y, it is even. Symmetric to the origin, it is odd. That's easy to remember because origin and odd, okay? Origin and odd, both start with O's, right? Okay, so you just have to remember y is the other one. Symmetric to the y-axis, it is even, all right? So once you've done your test for symmetry, you can tell if it's even or odd, all right? And so the examples they gave us, when we plug in the negative x and negative y here, you end up getting symmetric to the origin. So this one is going to be odd. When you plug in a negative x here, you get that it is symmetric to the y-axis. So you're going to get that that is even. And then this last guy, when you plug it in, it's not symmetric to y or to the origin. So that's neither. It's not even or odd, okay? So once you test for symmetry, once you know what it's symmetric to, you can immediately tell if it's even or odd. Y symmetry is even, origin symmetry is odd, all right? So as long as you know how to do that first example and plug in your negative x, negative y's, then you'll be able to answer if it's even or odd, okay? Questions on that?